Welcome back students to another video lesson from the chapter Gravitation. Today we shall focus on the discussion of three important topics from the same chapter. First being gravitational field, the second being intensity or strength of gravitational field, and last but not the least we shall study about gravitational potential energy. So let's quickly begin today's discussion with understanding what is gravitational field. The gravitational force between two masses, or the electrostatic force between two charges, or the magnetic force between two magnetic poles shows its effect even when they are at a distance from each other. For this reason, the gravitational, electrostatic and magnetic interactions are sometimes called as actions at a distance. Each of the three types of interactions can be successfully explained in terms of the field concept. According to the field concept, a material body, when placed in space, sets up the gravitational field. In other words, it modifies the space around it in some manner. So we can say that the space surrounding a material body in which its gravitational force of attraction can be measured is called its gravitational field. It is because of the gravitational field of the body that it exerts force on the material body that is introduced in its field. Intensity of gravitational field. The intensity of the gravitational field of a material body at any point in its field is defined as the force experienced by a unit mass placed at that point, provided the unit mass itself does not produce any change in the field of the body. So it is defined as the force experienced by a unit mass, which might be also called a test mass, placed at that point where the intensity is being measured, placed at that point, provided the unit mass itself does not produce any change in the field of the body. It is a vector quantity which is denoted by E. Now, the intensity of the gravitational field of a body is also known as the strength of the gravitational field, or simply gravitational field of the body. Since intensity of the gravitational field is force experienced per unit mass, so its SI unit is Newton per kg. Now let us find out the intensity of a gravitational field at a point due to Earth. Let us consider the mass of Earth to be given by m. If we are trying to find out the intensity of the gravitational field due to the Earth at a point P, which is at a distance r from the center of the Earth, then we will place a small test mass m at P, which is the observation point. So according to Newton's law of gravitation, the gravitational force that is existing between the two masses is given by F equal to gmm by r square. Now, as per definition of intensity of gravitational field, it is equal to F divided by m, so that will be equal to gmm by r square divided by m. So on cancelling it out, we get intensity to be equal to gm by r square. The direction of the gravitational field at the point P is along PO, that is, the gravitational field is directed towards the center of the Earth. It follows that the intensity of the gravitational field decreases as the distance increases and becomes zero at infinity. Now, in this equation, gm by r square is equal to the acceleration due to gravity at the point P. Therefore, we can say that intensity of the gravitational field at a point is equal to the acceleration due to gravity at that point. In other words, when we say that the gravitational field at a point is gm by r square, it implies that a test mass placed at that point will accelerate towards the Earth with acceleration gm by r square. The gravitational field at a point on the surface of the Earth can be obtained if we substitute small r equal to the radius of Earth. Therefore, the gravitational field at a point on the surface of Earth is given by equal to gm by r square, which is actually equal to acceleration due to gravity. Small g stands for acceleration due to gravity at the surface of the Earth. Now, if Earth is a sphere of material of uniform density rho, then we can write down mass of Earth m to be equal to four by 3 pi r cube rho. By substituting this value of mass in the equation for intensity of gravitational field, we get on the surface of Earth E gravitational to be equal to g into 4 by 3 pi r cube rho divided by r square, and that turns out to be equal to 4 by 3 pi g r rho. So this is the expression for intensity of gravitational field due to the surface of the earth, due to the earth on the surface. Next, we shall study about gravitational potential energy. Whenever two material bodies are present at a finite distance apart, the system possesses potential energy. It is because some work must have been done for bringing the two bodies from the positions where they do not exert any force on each other, that is, when they are infinite distance apart, to the present positions. The potential energy is positive if the two bodies are brought against the force of repulsion, and negative if the force between them is attractive in nature. So in case of two material bodies, this potential energy is called gravitational potential energy. We shall calculate the gravitational potential energy of a body situated at a certain distance from the center of the earth. But prior to that, let us define what is gravitational potential energy. So the gravitational potential energy of a body at a point is defined as the amount of work done in bringing the body from infinity to that point against the gravitational force. So when the body is at infinity, the gravitational potential energy is zero. It is called zero level of potential energy. Now let us assume that Earth is a uniform sphere of radius r and mass m. We have to determine the gravitational potential of the body of mass m lying at a point A such that OA is equal to R. By definition, the gravitational potential energy of the body at the point A, U, if we denote it by U, then it should be equal to work done in bringing the body from infinity to point A. Suppose that at any instant the body is at point P, such that OP is equal to X. Now let us mark the position for infinity. Then the gravitational force on the body at point P, the gravitational force of the body at point P is given by F equal to gmm by x square as per Newton's law of gravitation. The small amount of work done in moving the body through infinitesimally small distance P Q. Now suppose this distance is dx. Then the small amount of work done dw will be equal to F dx, force into displacement, and that will be equal to gmm by x square into dx. Therefore, work done in bringing the body from infinity to point A, work done in bringing the body from infinity to point A will be given by W. We have to integrate this expression over the limits. So that will be gmm by x square to dx. Now, as we all know that we can take out the constant terms out of the integral sign. So now we can write down work done to be equal to, we take out the constant terms outside, and the integral is with the limits infinity to r, we can write down x to the power minus 2 dx. So now we need to carry out the integration. So this will turn out to be equal to work done, W is equal to gmm. So on doing the integration, we get x to the power minus 1 by minus 1, and obviously we have the limits infinity to r. So now it turns out, on substituting the limits, we can take out the negative sign. So minus gmm, and it will be 1 by r minus 1 by infinity. So work done becomes equal to minus gmm by r. This work done is stored inside the body as its gravitational potential energy. Therefore, the gravitational potential energy U of the body of mass m at distance r from the center of the earth is given by minus gmm by r. This equation implies that on the earth we are in a negative energy. As with an actual well, work done must be done against gravity to get higher in the well. The gravitational potential energy of the body increases, that is, it becomes less negative as it moves higher. The top of the Earth's gravitational well is at infinity, where the gravitational potential energy by choice is 0. From this equation, it follows that the gravitational potential energy of a body at a height h above the surface of the Earth height h above the surface of the earth is given by u equal to minus gmm by r plus h. Now let's try to draw some conclusions from this result. In this equation, the negative sign shows that the potential energy of the body is due to the attractive force due to the earth on the body. That is, to bring the body from infinity to a distance r, work is done by the gravitational field of the earth. Now, as the distance increases, as the distance from the center of the earth increases, the gravitational potential energy becomes less negative, that is, it increases. So the gravitational potential energy becomes zero, that is maximum value. Maximum value of gravitational potential energy is zero when r becomes equal to infinity. So at infinity, the gravitational potential energy is attaining the maximum value, that is, it becomes zero. Now, if a body of mass m is moved from a point at a distance r1 to a point at a distance r2, in this case r1 is greater than r2, then change in potential energy of the body will be given by delta u, and that is equal to integral from r1 to r2 we will carry out the integration. So this will be again done in a similar way. So we will get minus gmm over the limits r1 to r2. On substitution we will get 1 by r2 minus 1 by r1. So that will turn out to be, if we include the negative sign inside the brackets, we will get 1 by r1 minus 1 by r2. So therefore delta u will be equal to gmm by r1 minus gmm by r2. As r1 is greater than r2, the change in potential energy of the body will be negative. It means that if a body is brought closer to the earth, its potential energy decreases. Now, in case the body is moved from a point at a distance r1 to a point at distance r2, where r1 is less than r2, then change in potential energy of the body will be positive, but its magnitude will be same as given by this equation. Now, in case the body is moved from the surface of the earth, this means r1 is equal to r, to a point at a distance h above the surface of the earth, this means r2 is equal to r plus h. Then, according to the previous equation, change in potential energy will be given as delta u. We have just now written delta u to be equal to gmm 1 by r1 minus 1 by r2. So this will be delta u equal to gmm 1 by r1 minus 1 by r2. So let us substitute the values for r1 and r2. So we will get gmm 1 by r minus 1 by r plus h. So this can be written in a modified form as gmm by r, and inside we will get 1 minus r by r plus h. So now expanding by binomial theorem, we will get delta u to be equal to gmm by r, and carrying out the expansion for the term inside the bracket. Carrying out the expansion for the term inside the bracket, we will get 1 minus Now at this point I would like to tell you that we can do a little bit of modification in this equation. If we are writing it down as delta u to be equal to gmm by r, and inside we get 1 minus 1 by 1 plus h by r, so that will give us delta u to be equal to gmm by r 1 minus 1 plus h by r to the power of minus 1. Thereafter we carry the binomial expansion, so we will get this step. Now in case h is very small as compared to the radius of the earth, the factors containing higher powers of h by r can be neglected. So therefore we get delta u to be equal to gmm by r, and inside you get 1 minus 1 minus h by r. So finally you are left with gmm by r square into h. Now as you can see that gm by r square, this particular term is actually acceleration due to gravity. So we can write down delta u to be equal to m into g into h, since g is equal to gm by r square. So it may be pointed out that the above equation holds only when the value of g does not change over the distance h. So we will end our discussion for today at this point. We shall continue with the other topics in this chapter in the next video lesson. Thank you.